Hi everyone, welcome to part 2 of our video lectures for section 11.3 on Taylor series. In our previous video, we went over the definition for a Taylor series and mentioned that in order for a Taylor series to be useful, we needed to know two things: the values of x for which the Taylor series was converging. And in our last video, we went over a couple of examples, and we saw here that depending on where you were centering your Taylor series, you could have different interval of convergences. But then we also mentioned here that in order for the Taylor series to be useful, you needed to know the values for x on which the Taylor series for f was equals to f. And that's what we're going to be taking a look at right now. And in order to know that, we need to know about the convergence for a Taylor series. So this is what we have. Let f have derivatives of all orders on some open interval I containing a. The Taylor series for f at a converges to f for all of x in I if and only if the limit as n approaches infinity for the remainder of the Taylor series is equal to 0 for all x on that interval, where the remainder here is given by the nth plus 1 derivative at c all over n plus 1 factorial times x minus a raised to the n plus 1. Now you might be thinking, wait, this looks familiar. And it should, because we've already discussed this concept in video recordings for section 11.1. There we go here. So this is how we obtained the remainder for a Taylor polynomial. We said that the remainder was the difference between the function and the polynomial approximation. Now what we're going to be doing in this section is really no different. So let's take a look here. All right, so in trying to show that the limit as n approaches infinity for the remainder for a specific function is equal to 0, we use the following theorem known as Taylor's inequality. If you have the absolute value of the n plus 1 derivative at c, if this one here is less than or equal to some m value for some radius of convergence, then the remainder here is going to be satisfying the following inequality. The absolute value of the remainder is going to be less than or equal to m divided by n plus 1 factorial times the absolute value of x minus a raised to the n plus 1 for some radius of convergence here. Now, as we're going to be evaluating some limits, I want you to know a special limit here that's telling us the following. The limit as n approaches infinity for x to the n divided by a factorial is equal to 0. It's going to come into play in a couple of problems. All right, so let's take a look at one problem here. And as I mentioned, this is really no different than estimating the error for a Taylor polynomial. It's just that this time around, we're going to be taking the limit, and if the limit for the absolute value of the error is 0, or for the remainder is 0, then you know that the series will converge to the function. Alrighty, so for this one here, we want to show that the Maclaurin series for the cosine given here is converging to the function f equals to the cosine of x for all x values. Okay, so I'm going to go ahead and use Taylor's inequality and take the limit as n approaches infinity. Okay, now a couple of things to do here. Since we're dealing with a Maclaurin series, we know that a is equal to 0, so this one here is just going to be a 0. And also, like I would say, the most important part for this type of problems is to figure out what is this m value. Now remember, the m here was defined as a value, some number that's greater than or equals to the absolute value of the nth plus 1 derivative at some x. Okay, so we have here that the m is greater than or equals to the absolute value of the nth plus 1 derivative evaluated at x. Now for this x here, remember the x is referring to the values that our power series would work for, or would work with when it's the interval of convergence. Now for this particular problem, we're being told that the interval of convergence is going from negative infinity to infinity, because we know that the cosine converges everywhere. So this one here, I'll just put here for x, in between negative infinity and infinity. Now, in some problems, we might be more mindful of whatever this x might be, but for this one, I don't think it's going to matter all too much, because think about the function that we're working with. We have the function that's a cosine, and the thing about the cosine here is if you were to take a derivative, you would either get, and because depending on the number of times you're taking the derivative, you're either going to be getting a cosine or a sine. So I'll just put here the absolute value for the nth plus 1 derivative at x is either going to be the absolute value of a cosine or the absolute value for a sine. Now, since we're looking for the highest points, we know that the cosine and the sine, they're always alternating, or they're always oscillating between a negative value of 1 and a positive value of 1. That's the highest and the lowest that they go to. However, since we're taking the absolute value, this one here has a max value of 1, and this one here has a max value of 1 as well. So therefore, the nth plus 1 derivative of x at x for a cosine function, it's always just going to be 1. So then, what we're working with in this Taylor inequality is the following. We're taking the limit as n approaches infinity for the absolute value of the remainder is going to be less than or equals to the limit as n approaches infinity for 1 over n plus 1. And I just realized something here, guys. I'm missing the factorial. So I'll put the factorial here. There we go. N plus 1 factorial times the absolute value of x minus a, which was 0. So the absolute value of x raised to the n plus 1. Okay, now this one here looks like a tricky limit. However, we have a special limit defined here that tells us that the limit as n approaches infinity for x to the n over n factorial is just 0. And that's precisely what we have here. We have the absolute value of x raised to this time around it's the n plus 1, but it's not going to change anything, divided by the n plus 1 factorial. And this one here is a special limit, which is 0. And there we go. What do we have then? We have the limit as n approaches infinity for the absolute value of the remainder is less than or equals to 0. But what do you mean less than or equals to 0? Because it's an absolute value. It's a distance. And we know that the distance is always positive or 0. So what we have here is then that the limit is 0. So that's what we wanted. Because we now know then that if the limit as n approaches infinity for the remainder is 0, then you know that our power series representation, or Taylor series representation to be specific, converges to f. So this one here, we can just end it here by saying, therefore, the power series for cosine, given here by the power series as n goes from 0 to infinity for negative 1 to the n times x to the 2n over parentheses 2 to the n factorial, converges to the cosine function. And there we go. That'd be it for this problem. And again, it's very similar to the problems that we did in section 11.1. The trickiest part is determining an m. What is the highest possible value that you can get for one particular derivative? A lot of the times, we can make use of the fact that we know that a function is either increasing or decreasing monotonically to figure out either the highest point and the lowest point to select our m. Okay. So this is it for chapter 11, guys. Hopefully it's something that you will keep on using for your later careers. Alrighty. Well, that's it. Have a good one.